Richard Wolff Jacobson is a software engineer and hobbyist designer with a passion for astronomy, vintage electronics, and unusual form factor computers. He's been observing the night sky for over 30 years with various commercial and home-built scopes. He hosts several code repositories on GitHub for projects like the very useful PiFinder, a portable DIY Raspberry Pi-based project that makes any telescope a push-to-telescope without modifying the scope or mount with sensors, etc., along with plenty of other features.
Yeah, thank you, Bart and Jack, for arranging and generously hosting me again. I had a great time back in March when I gave a presentation before, so I'm really excited to be back. Um, yeah, hi everybody. I am Richard Wolff Jacobson. Thanks for the intro. It's pretty much what I had on my slide here. But I love amateur astronomy and electronics and building stuff. And I think this presentation will cover a little bit of all of those things. This journey has sort of led me to think about how people have been describing the sky and communicating that, finding things in the sky. It's just been sort of a passion of mine, for many, many years, culminating in some of my recent work on plate finding and so forth. So um, I'll walk you through a little bit of what I've discovered. This isn't really a history per se. It's just kind of an exploration of how people's understanding of the sky and communication about the sky has evolved over time. It's definitely biased towards stuff that I thought was interesting, so it is not comprehensive, and there will be big gaps in things that I leave out. But I hope you find it interesting, and I think it kind of pulls together a couple interesting threads into where we're at with modern tools. So I'll be covering, general patterns in the sky, pictures that people have drawn or painted or recorded of the sky, the way that they've tried to understand, positions in the sky through coordinates, then get to computers and plate solving that sort of pull all of those things together. So we'll start with patterns. The simplest sort of a pattern is an asterism, some collection of stars that seem distinct for some reason in the sky. They're visually separated from other things. They're bright. They're recognizable. These tend to be fairly universal. People look at the sky, and various humans will sort of point at the same thing and be like, "That feels like a thing there. That deserves a name or some other recognition." A lot of our asterisms have centered around stars or patterns of stars, but there's also dark voids, especially in the galactic center of the Milky Way, and some people and societies have identified those as patterns worth naming and tracking. When a pattern has enough sort of cultural salience that maybe there's a story around it, or it becomes a little reified, people start to think of it as a thing distinctly. That's kind of a constellation. So they have a shared cultural significance oftentimes. Historically, they've been very much tied to religious or agricultural uses. And you'll see the same asterisms, the same patterns that humans recognize, identified or sometimes built out in different elaborate schemes across cultures. So the three stars that make up Orion's belt is a really common sort of feature that have been rearranged and have different narratives connected to it throughout time. Some of these constellations have taken on particular meaning when they appear at certain times in the sky. Taurus often marked the start of a growing season in sort of cultures that were in a certain geographic area. The emu, which is a dark patch of the Milky Way to the Australian Aboriginal. I think it's interesting that when it sort of sits up and it looks like it's intersecting with the horizon, it's time to go and harvest emu eggs. They're kind of nesting season. So these have cultural significance, and they're the first form of, I think, humans communicating about patterns and the sky. Of course, at some point this was standardized. There's a couple different schemes, but the one that we predominantly use now was defined in 1922. 88 fairly equally sized constellations. There's a couple outliers that are especially large or especially small, but it was really an attempt to split the sky into manageable chunks. And it was sort of informed by a couple different cultural backgrounds, a mix of Middle Eastern, Greek, and Roman primarily. So almost as soon as humans started talking about the sky and creating stories around what they saw there, they started developing pictures. And it's debatable when the first true sort of representation of the sky that we have evidence for existed, but the Lascaux cave in France has some interesting markings that seem like they may tie to a couple constellations. You can see someone's interpretation here. They're not exact, but this could be, basically 19,000 years ago, one of the first attempts to, record in a sort of permanent form some view of the sky. Moving from there, the best real solid evidence we have takes a little while to develop. In ancient Mesopotamia, to 5,000 years ago roughly, we have this really clear depiction of certain constellations that were important to that culture, along with a sort of visual guide of when certain stars were going to rise in the different seasons. This is called the Mulapin, which is the name of a particular constellation. The Plough is the translation, and that was a pretty important constellation for this group. It's pretty big. It kind of encompasses Cassiopeia, Andromeda, and Triangulum in our modern sort of view. The Egyptians were also pretty prolific in their written records. This is a relief that they did dated around 500 BCE, but there's much earlier examples, 2,000 years before the Common Era. And this is essentially a planisphere that we may almost recognize today. The constellations are different for the most part, but you can sort of see the structure with the cardinal directions and the various constellations that you could find at different times of the year. So very, sort of schematic, not artistic, of course, but it had a sort of reality to it. You can see what they were kind of trying to get at here as a guide for other people. That sort of idea was refined, and just a couple hundred years later, we had much more sort of developed systems. This one is a page from the Almagest, which was 120 CE, so roughly 1900 years ago, something like that. And this particular work was the sort of astronomical reference for almost 1200 years, produced by Ptolemy, in fact. This catalog contained 48 constellations, so kind of half of what we modernly think of. So they were larger and sort of covered more ground, but this was the way that people thought about the sky for quite a long time in the Western world. During the European Dark Ages, there were a good number of sort of Islamic cultures that were also grappling with how to describe and record the sky. They ranged from artistic representations, like the one you see here on the left, to more sort of schematic, or what you might call, really strictly representational, or almost, scientific, or mapping of the constellations against a sort of accurate scale and so forth. So they did an enormous amount of work kind of cataloging and trying to record with great accuracy positions of stars. The Renaissance, of course, had a renewed interest in a variety of topics. You see a lot of religious interpretations during this time coming out of the European work. There was a large focus on the constellations themselves and astrology and their meaning. So you don't get as many, really specific things, but more like guides or ornate things like this tapestry, or religious meaning like this picture of people using the sky as a way to judge religious ceremonies. Eventually, we came up with a really solid and reproducible way to record the sky: photography. About 200 years ago, 1822 was the very first photograph, and not even 20 years later, we have this photograph of the moon So very quickly, people turn these cameras to the sky. 40 years later, we have this image of the Orion Nebula, passable. It took 51 minutes through an 11-inch telescope. It probably looked a lot like the Orion Nebula looked through that telescope if you put your eye up to the eyepiece. The technology was not fantastic, but it actually recorded images of the sky. Just a few years later, we get this effort, which is notable because it was probably one of the first photographs to show stars that you couldn't actually see through a telescope with your naked eye. So we're getting beyond the magnitude where humans were sensitive to these stars, and showing that there's maybe a lot more there to be seen than just what you could see, even with a really powerful telescope. So sort of unlocking this idea that if you took a 60-minute exposure, this was through a 36-inch scope at the time, so a pretty enormous instrument, you could get a sort of view that you could not achieve in any other way. Shortly after this, based on that sort of discovery, in 1887, a project started, really ambitious project involving 18 observatories worldwide. They hope to create a photographic atlas of the sky. This will be sort of a theme going forward. Down to magnitude 14. They didn't complete this work, but it was sort of the first attempt of trying to photograph every single region of the sky and make a real record, of these patterns that they've been observing for many thousands of years. And with that, we reach into the digital era. Not even 200 years later, we have incredible tools for recording, and otherwise. Oh, sorry, I skipped one. This is more modern photography, still analog plates. We're at a time in, say, 1949, 1958, where we have, very good emulsions, much better telescopes, and we're getting, full sky surveys. The Palomar Sky Survey is one of the notable ones. It covered pretty much the whole sky through 48-inch scope, and it took almost 10 years to complete. But I still use these plates honestly in my projects. I think they're a good representation of what you might see through an amateur scope nowadays. And then, yes, finally we get to the digital era, and what is there to say here? We're just bombarded by beautiful, incredible images from really skilled folks all the time. There's better, more sensitive sensors. There's better lenses, really good optical telescopes. There's better processing techniques. And we've done, a lot of work with that. We have the Sloan Digital Sky Survey that started in 2000 to cover the whole sky, create three-dimensional maps using parallax and other techniques. That's continued now, and they're on the fifth version of that, the Next Generation Sky Survey. And they're actually now recording differences in stars over time. So we're not only getting a static image of the sky, but they're taking images frequently enough that you can see variation in stars and so forth. So that's pretty incredible. It's sort of a big movie of the sky. And in terms of the data collected, we now have data sets like the Gaia data set with 1.8 billion stars that we've recorded with their exact position. We've been able to take photographs, identify exactly where they are in space. That's pretty incredible in roughly 150 years to go from that first image of the Orion Nebula that showed that there's sort of a hidden world out there to an actual catalog of 1.8 billion stars, that most of which, of course, you can't even hope to see with the naked eye. So as we started, collectively describing and drawing and recording the sky, very quickly we wanted to catalog and systematize this through some sort of coordinates. The Babylonians were one of the first to do this. We can lay the blame on them for astrology because they sort of developed this idea of these constellations around the ecliptic being important in a certain way. And so they, figured out that the sun follows this particular path through the sky, and they, plotted most of their observations and their sort of coordinates against that. So it was them that also started using degrees as a unit of measure to, describe the distances between different points in the sky. So they brought some mathematical precision to it, but their coordinate system was really much based around the ecliptic and the path of the sun through the sky. The Greeks were also kind of working on this at a later time, and they, instead of, you know, working on just the ecliptic base system, eventually Ptolemy defined this idea that you could take the surface of the Earth and kind of project it outwards, and so you could describe the crystal sphere, as they thought of it, of the heavens in a way that intersected with various points on Earth to describe a grid. And that's sort of our modern right ascension and declination, our equatorial system. Again, we come back to Ptolemy's Almagest, which was the sort of textbook for a long time. This is where this system of right ascension and declination was really solidified. There's 1,000 stars there with almost correct. You can quibble about the accuracy, but for the time, I think it's pretty impressive that they had, pretty decent position information for that many stars. And again, this was the textbook for thousands of years if you wanted to learn astronomy. In the modern era, we've expanded on this. We've refined our understanding of position into, arc seconds and arc milliseconds, very fine measures. We've understood now that the sky is not a static place, and the place where a star is today will not be where it was, many years ago or in the future. So now we're expanding, and we're talking about position not only as a point in time, but as this sort of continuum with proper motion. And now we have, proper motion for, again, that same 1.8 billion stars through either parallax or other mechanisms. So our modern understanding of position has taken this kind of richness that incorporates time in a way that past people just didn't have any way to really measure or understand. So that's where we're at in terms of describing where things are in the sky. And that kind of brings us to the role of computers. So computers are essential for cataloging all of this information that we have. 1,000 stars in a textbook is a pretty ambitious effort for a human being, but 1 million stars would just be beyond anyone's capabilities without some help. So computers not only allowed us to compile these larger compilations of positions, but there's also certain types of computers that help us actually point at things in the sky. And so the earliest example of this was setting circles. As soon as right ascension and declination was sort of solidified and telescopes became a little bit more commonplace, people oriented them, along the axis of the celestial coordinate system, pointing them at the celestial pole. And they, had setting circles, or these gradated circles that they could use to dial in a particular right ascension and declination. This was the solution for finding stuff for a good couple hundred years. It does require really careful alignment, though, to make sure that your axes are that they coincide with the celestial axis, and you need to continually adjust your scale to take into account the local sidereal time. And as you can see in these two examples here, you're really only going to be able to find a position in the sky as precise as you can determine from your scale and your markings. So, very large setting circles will let you get much more accurate. They have their own kind of awkward things, but this little dinky one that comes with some less expensive mounts, maybe you get a degree of accuracy out of that. So setting circles were the solution for a long time, until we came up with these digital setting circles. And essentially, they build on these encoder technology that was used in industrial manufacturing and so forth to understand units of rotation and monitor the actual mount as it moves through its range of motion. This uses a really interesting system of quadraturn coding for the most part. It's really interesting stuff. If anyone has any interest in how this stuff works, read in gray code and quadrature encoding. It's fun, but essentially, it's a way to simply and without a lot of expense build a system that can understand whether an axis is rotating one way or the other and how fast. And you count the number of sort of times that you see this pattern appear, and this lets you understand how the mount is moving. But you don't necessarily have the correlation of how the mount is moving with how that's actually changing its pointing position in the sky. So all of these systems that rely on setting circles need some way to mate the motion of the mount with actual stellar positions. And that's usually done through, pointing the telescope at a couple stars. You record the position of the digital setting circles, and you build a mathematical model which lets you go from one to the other. So if you know the positions of the two mount axes, you can then calculate where you think that's pointing in space and vice versa. This would be very difficult without a computer because, again, you need to continue to update this model as the sky turns overhead. So you need to track the time, you need accurate clocks. So, this sort of much simpler way for the end user, more technologically complicated, but a simpler way for the end user to point their telescope at a particular place in the sky was enabled and really made possible by computers. But it is still an indirect method, and it doesn't always get the right solution. So what if we could take a lot of what we've kind of talked about here and a lot of what humans have been doing, patterns in the sky, pictures of those patterns, coordinate systems in computers, and marry them together so that we can know absolutely what it is we're looking at in the sky. And that's plate solving. For anyone who's familiar with astrophotography, this is bread and butter. It's a great way to, uniquely know where you're pointing at in space. And it's essentially derived from the process that used to happen where people would compare plates together, physical photographic plates, thus the plate solving. And it's direct and it's accurate in as far as you can, perform this feat of finding some set of patterns on your plate in your image and comparing that with some known set of patterns, another plate, or, in more modern times, a database in a computer. And that can give you a very accurate and sometimes very fast idea of where you are in the sky. There's a lot of different ways to do this, and I'm going to talk through one way because I think it's kind of interesting how it pulls all of these threads together. But it's important to note that there are a lot of different approaches here. They have different trade-offs for accuracy and speed and so forth. They're all pretty accurate, but they have some trade-offs there. I'm going to talk about a methodology that is designed to be robust and accurate. It's sort of what has been used by the European Space Agency for their Lost in Space solver, which is essentially, I'm a satellite. I don't know which way I'm pointing. I have an image of the sky. I need to very quickly determine, am I pointing in the right direction? So the European Space Agency published their code, open source. It's called Tetra 3. Really cool piece of kit if you want to look at it. But I'm going to just describe here briefly kind of the steps that go into this because I think it's interesting. And again, it pulls together all these things. So the first step is you have an image. And to a computer, this is, a bunch of pixel values. And you need to figure out which one of these pixels or which group of pixels represent stars. That's generally referred to as centroiding or star detection. There's a lot of interesting stuff here with, especially for ground-based observations. You want to kind of ignore trees and other obstructions if you're doing plate solving from the ground. Sensors have these variations in their performance towards the edges, vignetting, and so forth. So there's a lot of interesting stuff that goes into here. But eventually, you want a flat, nice image that has the stars identified. Ideally, you also want some idea of their brightness because that helps you kind of with this pattern matching. And so that's what the detection phase is. And in modern computing, this is a pretty well solved problem. You can take a pretty high resolution image and you can centroid it in just a few milliseconds. And then you're faced with the problem of, okay, great. I know where the stars are in this image. How do I actually identify where it is? And so you can see here, we've gone from an image to a bunch of stars. These centroids essentially become a table of data. I didn't have a good representation of that, so I just replotted them as their intensity on a nice black field to show how much data has been extracted from this centroiding. But then what we do is we pick the 4 brightest stars in the field. It doesn't really matter what the field is, as long as we have their relative brightness, we can pick the four brightest ones. Out of those four, and you can see them identified here as 1, 2, 3, 4, we pick the two that are closest together. And we say that that's distance D. Whatever it is, you can measure that on the sensor by number of pixels. You just need some measure of that distance to start this whole kind of pattern matching process. Then you connect all the rest of those stars in every combination, and you express the distances between them as some multiple of that first distance. So it's always going to be greater than 1 because we picked the shortest one to be D. And so you can see here, we have all of the different connections of all those four bright stars, all with some multiple of D associated with them. We can then take this and sort of abstract this even further and just sort of run them together. So we can say that the first one is D, and then we have 6.2 D and 5.1 D and 1.5 D, and we can kind of line them up in a particular order. And we get this number, and we're starting to look more and more like a pattern that a computer could really kind of dig its teeth into and do some matching. And this pattern here that we get, essentially this string of digits that are the lengths of all these connections, becomes something that the computer can really find tractable and compare against a database. So this is ultimately what gets this pattern number, this hash, is what gets compared against a lot of other hashes until one of them kind of matches to some approximation. And then you usually verify that. You're like, okay, great. I think this is the right thing. I should expect to see these other stars. I do see these other stars. I have confidence that this is the correct pattern. The nice thing about this mathematical representation and this pattern construction methodology is that it doesn't really matter what orientation the stars are or even what scale they are, because this number is always going to be generated the same way, because you're starting with the two brightest stars that you can find. The four brightest stars, the shortest distance between them, that's always going to be the same, whether you're zoomed in on this, you're zoomed out, whether it's rotated. And so this pattern that's generated is, invariant to rotation and scale. So this works pretty nicely, even if you don't know how your satellite is oriented or how your telescope is oriented versus the sky. And that's one way of approaching this problem. Again, there are many other problems, but many other approaches, but this one is particularly fast if you don't have any information at all about where you might be pointing. To talk a little bit about what this feels like in practice, the PyFinder, which is an open source project that I developed and now sort of helm, we use a database built off of 18,000 stars down to magnitude 7. We focus on a 10-degree field of view because that's kind of the camera that we normally use. And that gives 712,000 patterns of these digital sort of fingerprints. 8.6 megabytes doesn't feel like much nowadays, but that would have been a lot, 20, 30 years ago. We can get down to magnitude 7, with just a very short exposure with modern sensors, less than, a 20th of a second, sometimes even less than that. And it can go through this whole process of detecting the stars, figuring out the pattern, matching the pattern against the database on relatively, inexpensive, not very powerful hardware in just a few milliseconds. So it kind of shows how far this technology has come from the days where people would, hand identify stars on plates and compare them against known references to try to figure out the right ascension and declination. We are in a truly a sort of magic and golden age where we can just do this on demand and use this as an actual tool for astrophotography and amateur astronomers who want to find something in the sky or verify that they found the right thing. It kind of pulls all of these different things together: patterns, coordinates, representations of the sky into a sort of complete package here. So that's just a little bit about, I think the interesting points in the history of celestial wayfinding. And with that, if this is interesting and it raised any questions for you, I'm happy to talk about this. as much as I can. Again, I'm not an expert. This is just my sort of interesting journey through this as I was learning about this stuff.
Cool. Are there any questions in the room? Are there any questions on the Zoom session? Is everyone awake? Everyone is awake. I had one, but I can't remember it. I guess I was curious on the 1800 photography image. I was wondering if you knew if that image was hand cranked. In other words, they had to, I don't know if there were clock drives on scopes that far back.
That is a very good question. I mean, this is clearly tracked. It took 60 minutes. So someone was
the one
moving
prior
the
to
scope.
that. The one prior to that, a little sloppier.
Yeah.
There we go. That one.
51 minutes. So, they didn't quite nail focus, it looks like. But the tracking looks decent. You got, that's a little bit of elongation. Yeah, I don't know if this was hand tracked. They had clock drives back then, I think. So, yeah, it's a great question. I will research it and add it to the presentation if I ever give this again.
Further questions in the room? John, did you have one? I'm about to walk through there, and if I do, I'm going to trip over the camera and fall on my face.
So the plate solving method it's just an abstraction. Like it's not really tied to anything, but the closest thing it's tied to is our sort of two-dimensional take on the sky, right? Am I right about that? It has no other, it's not attached in any value to anything else, any other, right? It's just an abstract process based on what we see. We're training the computer to see what we see and filter that. Is that accurate?
That is accurate. Half the trick is just figuring out how you can describe the pattern in a way that computers like. Because we've essentially, through this process, we've gone from, say 1024 by 1024 image with, say, 10-bit raw values for each of the pixels. That's an enormous amount of data. And we've distilled that down to essentially, what is this? A couple floating point numbers, maybe, a couple words of data here. That's the trick. And then once you're there, the computers are really good at matching and going through their memory and finding, does this number look like this number? But getting to the abstraction where you can have the computer perform that, I think is the tricky part. And it is very much based around our ideas of how you describe the sky. Like I would imagine that if we didn't describe stars the way that we do and we ascribe some real value to them, maybe there would be some other mechanism for identifying where you're pointing in the sky. But because it's for us the really salient part, we don't see radio, we don't see these other things, although we'd probably still get the stars at some point. But maybe you could use the cosmic microwave background radiation variation to identify a particular point in the sky if you had access to that. But because we like stars, we engineered this whole process, at least this particular one, around patterns of bright little dots on the image.
Thanks. Oh, another one in the room.
An observation here. As an ex-programmer, I'm looking at this and I'm wondering where else this technique might be used. Facial recognition, for example.
Any
knowledge about that?
No, but it's very interesting because this idea of using distances between landmarks gives you that scale and rotation invariance that you would want in facial recognition. Now, if I move my head a little bit, the distance between my eyes actually shrinks, and that's something we don't have to worry about when we're imaging something so far away. But I'm sure there's kind of variations on this same theme, and I wouldn't be surprised if so much of it boils down to just how do we describe this visual data in the shortest, most compact, unique fingerprint that we can. So I'm sure hashing of this nature comes into play there somehow.
I want to throw one thing into there too, because I used to work with databases that work with a hash, a similar thing. Your key value would become something similar to that. So we could call that a key, and then that's a unique lookup at that point. So, a lot of database systems will use a similar methodology. The only difference here is that this key is a relationship itself between 4 objects. And it's a unique relationship. Another question.
And if anyone's interested in the process of generating the database, you have to have, it comes into like, if you want a 10-degree field of view, you have to have a certain number of overlapping patterns, because you may get half of a pattern, or, so to generate this database, you're essentially simulating taking photos of the sky at a particular focal, field of view, cataloging those stars. So the process of generating the database is essentially, photographing the entire, virtual sky based on your catalog of stars, and generating all these hashes so that you can then find them later when you're actually looking at that pattern in the real sky. So that's another interesting bit about overlap and coverage and so forth.
Oh, this is definitely out of left field, but you used the term wayfinding, and you also talked a lot about historical models, and I was thinking about how ancient people got in a canoe in Polynesia and made their way to Hawaii I've heard, by looking at constellations and the stars. And I'm wondering if that's something that you've thought about, if you've looked into, or, if that's even on your radar. I know I see all the mathematical and the computer stuff that you're focused on, but I was wondering a little bit more about that historical wayfinding using constellations.
It's a good question, and I haven't explored that a lot. I've looked into sort of modern, equipment for determining latitude or longitude based on, the star patterns that you can see. That's a very, specific sort of more modern take on that. But I chose wayfinding as both a simple way to try to describe this idea of finding your way in the sky, but it does connect very directly to celestial navigation and wayfinding on Earth, which could be a whole nother talk. And I have not gone into that in any great detail, but I'm, if I had some more time, I'd be curious to know.
Oh, we got an answer to that.
Oh yeah.
All right, don't quote me on this. But in your specific example, Polynesians getting to Hawaii, they used Arcturus as a zenith star. And so if Arcturus went any number of degrees apart from the zenith, they knew that they had the correct course.
Interesting. Cool. Of course, they didn't have iPods, so they had a lot more time to study the stars. Further questions?
A better sky than most of us probably have as well. So.
Yes, exactly. Any questions out on Zoom session? No more questions in the room? Oh, wait, we do have one. Of course, it's as far away as it can get. So give me a second.
Well, thanks for hustling the mic around.
No worries.
Appreciated.
This may be a question somewhat off base, but my thoughts about this is how long, as far as these ratios and as far as locating various stars and identifying where they are by their spacing, would hold up as you move away from Earth. Because I'm talking about this and thinking about space travel and where that all of a sudden starts to fall apart.
It certainly will at some point. I'm not aware of the mathematics enough to say. This works for satellites. Clearly, they're pretty close to Earth. I would guess you'd have to go pretty far from from the sun before the parallax would start moving enough of these that the database, for instance, that the Pi Finder uses would no longer be satisfactory. Just because of the distances involved, you'd have to move a fair bit, I'd guess. But yeah, they would definitely break down.
Would it be good if you're still within the solar system, or if you would have to be beyond that?
I would guess it would be many, solar system measures, however you want to measure that. away before you'd see any real significant difference in the patterns. We see
Without-
parallax on some stars from one side of our orbit to the other, but it's measured in very small increments. So I think before it really became destructive enough to the patterns, you'd have to go pretty far.
We'll be talking several parsecs rather than several AU then, right?
I would think so, but it would be a good, I guess, introduction to the astronomy, I guess, quiz question
I guess
for someone to
us,
calculate.
the biggest change for us up here would probably be with Sirius, right? Because it's what, 8 light years away, and then Proxima Centauri is 4 and change.
You could probably simulate that.
It's
With the planetarium program, some planetarium programs, you can actually change your location, fly through space, and then use that screen, of kind of point a camera at the screen and see if you could confuse it. See
Yeah.
how long it takes. Yeah, you could do that.
That'd be cute.
Yep. Determine it
questions?
experimentally in a way. Yeah.
That's neat. I don't see any further questions in the room. All right, and no further questions, no questions on the Zoom session? I'm not at the computer, so I don't see if there's anything in chat.
No, I asked.
Okay, nothing in chat. So
Okay.
I guess that calls it then.
Well, thank you
so much, Richard.
Yeah, thank you.
Again. All right, beautiful. Thank you very, very much. With that, we'll close things out here. And Richard, maybe we'll get to see you again in a few months.